Deciding which moments to remember and which to discard is a key capability of an intelligent system. We remember what is important and forget what is uninteresting or redundant. Thus, memorability is a measure of the importance of visual information. If a system can predict which content is memorable, it can evaluate the quality of incoming data and choose content to retain and prioritize. In this work, we build towards this goal of creating a computational model of visual event memory. We build Memento 10K, the biggest video memorability dataset to date that contains both human annotations at different viewing delays and human written captions, making it ideal for studying the effects of delay and semantics on memorability. Based on this data, we propose a mathematical formulation of memorability decay that allows us to estimate the probability that an event will be remembered at any point over the first 10 minutes after viewing. Finally, we introduce Semantic MemNet, a multimodal model that relies on visual and semantic features to predict the decay in memory of a short video clip. It is the first model that predicts the memorability decay curve, and it achieves state-of-the-art performance on 2 video memorability baselines. My name is Annalise Newman, and I'll be telling you about this work I did with my colleagues at MIT as part of the Memento project. 4 landmark results in cognitive science informed this work. First, memorability is an intrinsic and consistent property of an image. Second, semantic features boost visual memory and aid in predicting memorability. Third, most stimuli decay predictably in memory over time. Finally, the classic old-new recognition paradigm allows researchers like us to collect human memory data at a large scale. In the computer vision community, Isola et al.'s seminal work showed that image memorability could be predicted from an image's pixels. This finding applies to a large variety of image categories. The introduction of large-scale datasets like LawMem paved the way for CNNs to approach human consistency for memorability prediction, and algorithms can now generate memorable and forgettable images. However, large-scale work on video memorability prediction is more limited. Cohendet et al. Introduced VideoMem, a video-based memorability dataset, and made progress towards building a model of video memorability. Other works in this space have largely relied on smaller datasets. So we create the Memento 10K dataset. It is the biggest video memorability dataset to date, with 10,000 video clips and nearly 1 million human responses. It focuses on both the visual and semantic underpinnings of video memorability by including memory scores, action labels, and textual descriptions for each video. Importantly, our memorability annotations occur at a variety of presentation delays, which allows us to model how memorability falls off with time. To collect memorability scores, we create the Memento Game. In this game, a participant watches a stream of 3-second videos and presses the spacebar when they see a repeat. We keep track of whether a participant detects each repeated video. A video's hit rate is the fraction of times a video was correctly identified as a repeat. We also keep track of the lag at which the video was shown, the number of intervening videos between the first and second presentation of the repeat. Importantly, our lags range from 9 to 200 videos, about 30 seconds to 10 minutes, which allows us to study how memory falls off over time. Our memorability data shows some similar patterns as with image memorability. Memorable videos tend to contain saturated colors, people and faces, manipulable objects, and man-made spaces, while less memorable videos are dark, cluttered, or inanimate. Occasionally, videos with interesting motion patterns can be highly memorable, whereas static videos often have low memorability. Because Memento 10K's annotations occur at a range of lags, we have the opportunity to calculate the strength of a given video clip's memory at different delays. If we plot a video's hit rate as a function of lag, we should see that as lag increases, the hit rate decreases. However, we find some surprising patterns in the Memento data. First, for the lags that we studied, we observed that hit rate decays linearly as a function of lag. This is notable because previous work has found that images follow a log-linear decay curve. In this figure, the blue line plots our raw annotations, and the orange and green lines show a linear and log-linear best fit line respectively. The linear trend fits our data better. Second, prior work from Khosla et al. Assumed that all videos decayed in memory at the same rate. We instead assume that videos decay in memory at different rates. We can see that videos with lower memorability, like the purple line at the bottom, show a faster rate of decay than videos with higher memorability, the yellow line at the top. So, how do we calculate the memorability scores for each of our videos? Based on our findings that video memorability falls off linearly with time, we model memorability as a linear function of the lag, where the hit rate of a video, v, at lag t, is equal to a decay rate alpha times the lag plus a constant. If we know the video's memorability at one lag, which we call uppercase T, then we can use that memorability value and the decay rate alpha to calculate the score at a different lag. In this way, we can describe the memorability decay curve using two values: a memorability score, defined as the hit rate at a particular reference lag, uppercase T, and alpha, the decay rate. We choose a lag of 80 as our reference lag, and thus define a video's memorability score as its hit rate at lag 80. To obtain values for a video's mem score and decay rate, we minimize the L2 norm between the raw annotations from our experiment and the predicted memorability score at the corresponding lag. More details can be found in the paper. Finally, we explore different architecture choices for modeling video memorability that take into consideration both visual and semantic features. We also develop the first model that predicts a video's decay curve instead of a single memorability value. First, we study the extent to which visual features contribute to memorability. We train 3 different streams. First, an image-based stream that operates on individual static frames. Next, a video-based stream that operates over the entire video, which allows the network to access information on both motion and visual features. And finally, we train an optical flow network that serves to isolate the effects of motion. Here are our results for Memento 10K and VideoMem. For both datasets, optical flow achieves the lowest performance, probably because of the lack of access to explicit visual features like color and shape. Static frames perform remarkably well on their own, outperforming a 3D video representation on VideoMem. Even with the relatively high level of motion in the Memento 10K dataset, the video and frame streams perform comparably. For both datasets, combining the 3 streams maximizes performance. Next, it is well known that semantics are an important contributor to memorability. To increase our model's ability to extract semantic information, we jointly train it on memorability prediction and a captioning task, which ensures that the underlying representation contains relevant event semantics. To test this approach, we enhance the video stream from the previous section with an additional module that aims to solve one of 2 tasks. The first option is to predict captions directly by injecting the feature vector from the video encoder into an LSTM. The second option is to learn to map the video into a sentence-level semantic embedding space, which we train using a triplet loss. We find that caption generation outperforms the semantic embedding approach on Memento 10K and provides a boost over just using the video stream for both datasets. Finally, we explore methods for predicting the memorability decay curve instead of a single memorability value. The first option we consider is called a mem-alpha model, which produces 2 outputs by regressing to a video's memorability score and decay rate alpha. These values can be used to construct the memorability decay curve. The second option is a recurrent model that directly outputs multiple probability values corresponding to different points on the decay curve. We find that the recurrent decay model is better at predicting the raw memorability values, while the mem-alpha model has better performance in terms of rank correlation based on ordering the videos by memorability score. Because of its relative simplicity and strong RC score, we use the mem-alpha architecture for our final predictions. Our final model, Semantic MemNet, combines our findings. We use a 3-stream encoder that operates on 3 different input representations. We jointly train the video stream to output memorability scores and captions, and each of our streams predicts both the memorability score and the decay rate, which allows us to predict the probability that an observer will recall the video at an arbitrary lag within the range we studied. Our model strongly outperforms previous approaches for video memorability prediction on both Memento 10K and VideoMem. Semantic MemNet is the first model that can predict the entire decay curve for each video. Here we show some examples of its output, where we plot the predicted memorability decay curve based on Semantic MemNet's values in purple and the ground truth in gray. Video memorability models open the door to many exciting applications in computer vision. They can be used to provide guidance to designers, educators, and models to generate clips that will be durable in memory. They can improve summarization by selecting segments likely to be retained, and they can act as a measure of the utility of different video clips in space-constrained systems, for instance in a live stream in a pair of virtual assistant glasses. Predicting visual memory will lead to systems that make intelligent decisions about what information to delete, enhance, and preserve. You can find more information about this project on our website, memento.csale.mit.edu. Thank you.